Hey, good afternoon. This is Math 2413, and today's the last lecture of the semester that I'm going to post. The topic we're going to cover is area between two curves. This is a topic that I think is important as you head into Calculus 2, that you see a few examples and kind of have a decent sense of what this entails as far as setting up integrals for finding area bounded by several curves. So we're going to go through that, go through some introductory examples. You will see a problem like these on your final exam. So I just wanted to get a lecture posted out there so that all of you could at least see a couple of problems worked out and also kind of see the mathematics behind this topic. All right. So the idea is this. What we're doing is if we identify two functions, and let's say we have a function f that looks like that, and a function g that maybe looks like this, and we identify some x values, let's say a right there and b on the x-axis like that. How do we find the area of the region that's bounded between these two graphs, right? This is the region that we're talking about right here. And what we want to do is find the area bounded by by these two curves between A and B. Okay, so what I want to do is walk through how you would think about this kind of problem and how you would set up the integral. And we want to do this in such a way that we can extend this idea to different situations. All right. So now what I recommend for my students is to identify an approximating rectangle, a typical approximating rectangle, and that's what I'm going to refer to it as. And we're just going to talk about the left edge, because that's the way we did it in class. The left edge of this rectangle is determined by these two functions. And so let's say that this left edge is at the x value x sub I, okay, x sub I. So what we want to do is write down the expression for the area of that rectangle. So that's what we're looking at, is the area of that rectangle, and then we kind of go through the limit of the sum process and we end up with a definite integral. But it's important to be able to kind of zero in on this one rectangle and see how this is going to work out. All right, so first of all, if we're going to try to find the area of this rectangle, we need to talk about the width of the rectangle. So the width of the rectangle would just be delta x. Technically, we might write delta x sub I there for the width of the ith rectangle, but remember, we've talked about that we're going to make a simplifying assumption here that these rectangles all have the same width, which in fact doesn't have to be true, but it just makes things simpler for us as we walk through it. All right, so now the height of this rectangle is what we're interested in particular here. The width is no big deal. That's not really a change from anything we've done in the past. But the height here for this rectangle, it'd be nice if I could spell the word height correctly. There we go. So the height of this rectangle, well, if you look at your picture right here, this distance right here, okay, that lower function there is g, and that distance would be g of x sub I. Okay, like that. And then, if we looked at this distance right here, I'm going to draw this arrow on the other side of the rectangle just to give us some room there. But again, it's the left edge, which is x sub I, and it's that function value. So that distance would be given by f of x sub I. And so the height of this rectangle, would be, on the picture, would be this distance right here. And the height of this rectangle would simply be f of x sub I minus g of x sub I, like that. And so that would be the height of our rectangle. The height of the rectangle, of this ith rectangle, would be f of x sub I minus g of x sub I. And what I want to point out here is that represents, just if you look at the picture visually, this is the upper curve minus the lower curve. All right, so when we use those widths and those heights, and then we go through the limit of the sum process, we end up with this expression. And so there's a major dot, dot, dot right here, right? We're skipping a lot of steps here. But we go to the definite integral. We end up with this definite integral of the integral from a to b of the upper curve f of x minus the lower curve g of x dx. And that quantity gives us the area bounded by those two curves. Now, I want to draw a couple more pictures here because that picture, both of those curves, f and g, are both above the x-axis. So what if the curves weren't both above the x-axis in the interval that we were interested in this case, the interval from a to b? So what if one of the curves was above the x-axis and the other one was below the x-axis? Does that make a difference? Okay, so let's say here's our function f. See, so this one's above the x-axis, and this one is g. That one's below the x-axis. We're looking for the area bounded between a and b, right? So we're looking at the area of this region, and I'm going to shade this in. Okay, so the difference here is that in the interval between a and b, one of the curves sits above the x-axis, one of them is positive in that interval, and then the other one sits below the x-axis, and the other one's negative in that interval. Okay? So there's our region. All right, so we look at an approximating rectangle, just like we did in the last picture. So here's our approximating rectangle, and let's say we put it right here. There's our x sub I, and so we're using the right edge. I think I may have said left edge on the previous picture here, but we're using right edges here. And so here's my approximating rectangle. We're using right edges when we draw this picture out. This is our x sub I right here. And so we want the total height of that rectangle. So now this distance right here for the curve above the x-axis, that piece of that rectangle, it's that distance there would be just f of x sub I. And then for g, this piece of this rectangle, that distance would be g of x sub I. Now, one thing I want to point out is because that piece of the rectangle is below the x-axis, g of x sub I is a negative number. And so what happens when what we were trying to do is see if there's any difference in trying to find that total height, right? The total height in this picture would be represented by this distance right here. This would be our total height. And would that total height still be the upper curve minus the lower curve? And the answer here is that yes, it would, because remember that g of x sub I is a negative number, right? This is a negative number right here because that curve is below the x-axis. That's a negative y value. And so what happens? You're subtracting a negative number. And when you subtract a negative number, what do you end up doing? You end up adding, and you end up with the distance there. Let's pretend for a minute, pretend that f of x sub I is equal to 6, and g of x sub I is equal to negative 10. Then notice what I would get. If I looked at f of x sub I minus g of x sub I, I'd get 6 minus negative 10, which would be 16, and that would be the total height of that rectangle, right? In my picture, this would be 6, that distance, and that distance, or that y value rather, would be negative 10. And sure enough, that total distance would be 6 minus negative 10, or 16. And so I do get the right height, and so in this picture, the area is still upper curve minus lower curve. So nothing changes in this situation. So nothing changes here. And so the area is still given by the integral from a to b of f of x minus g of x dx. It is still upper curve minus lower curve, even if one of the curves is above the x-axis and the other one is below the x-axis. All right, so now the third possibility here that we want to talk about is what if both curves sit below the x-axis? What if both of them are negative? So here's f, and here's g, like that. All right, and so there's g, and we're trying to find the area bounded between x equals a and x equals b. So we're looking at this region like this, and again, I'm going to shade it. So we're trying to find the area of this region. Okay, and so we identify, again, a representative rectangle inside there. And so we'll say that this is our representative rectangle. We're using right-hand edges here to determine the height. And again, if we say that that's x sub I right there, then what do we have here? That f of x sub I on our picture represents this distance right here. That's f of x sub I. And what do we know about f of x sub I? It would be a negative number. And then here is g of x sub I on my picture. G of x sub I would be represented by this distance, like so. And what would g of x sub I be? It would also be a negative number. So let's pretend again here that, so let's pretend for a second that f of x sub I is negative 5, and g of x sub I, well, now the distance g is greater than the distance f, so this should be a quote-unquote bigger negative number, right? A negative number with a bigger absolute value. So let's say that this is negative 12. All right, so if we know that's true, if we know that this y value is negative 12, and this y value here is negative 5, then clearly this picture right here, in this picture, the height of this rectangle would have to be 12. I'm sorry, 12. I lied. It would be 7. All right, and what happens when you take upper curve minus lower curve? If I take negative 5, which is the upper curve, the y value for the upper curve, minus the y value of the lower curve, notice you do, in fact, get 7. And so the area of this region is also exactly like we've been writing, so nothing changes again. And so the area of this region would still be the integral from a to b of f of x minus g of x dx. So this is great, and that's upper curve minus lower curve. And like I said, this is great because this means that it doesn't matter where the curves are in relationship to the x-axis, whether they're above or below, or sometimes above, sometimes below, that if you're looking for the area between two curves like this, that it would always end up being the upper curve minus the lower curve. So with that in mind, then, we can attack some of these problems like this. All right, so let's look at some examples here, and then we're going to have to look at a few issues as we go through this. Excuse me. So let's look at this example. And so the example is to find the area bounded by the function f of x equals 9 minus x squared and the function g of x equals x plus 3. So notice this is not, we're not given two x values and saying, okay, find the area bounded between those two, by the curves in between those two x values. This is just the region bounded by the two curves. And so one thing we must do is we must find where these two curves intersect. So we must, because that's certainly implied from the directions here, is that there's a region that's bounded by these two graphs. So we must find the point of intersection. And I'd say points of intersection. Okay, and so we can do that using substitution, right? We've got y equals 9 minus x squared, and we've got y equals x plus 3. So we simply substitute and use substitution here and substitute one of those equations in for y in the other equation. And so when we do that, we get x plus 3 equals 9 minus x squared. What a lot of you will say is I'm just setting the two equations equal to each other, right? And that's because both of them are solved for y, and you're using substitution to solve the equation. Okay, so this is a quadratic equation. I add x squared, and I have x squared plus x. I subtract 9, and I get x squared plus x minus 6. And so we get an easy quadratic to solve because this is easily factorable. So you have x plus 3 times x minus 2. And so I get two x value solutions, negative 3 and 2. So I'm going to get 2 points of intersection. And then I use y equals x plus 3. And I get, when x is negative 3, I get y is 0, which gives me a point of intersection at negative 3, 0. And when I use x plus 3, y equals x plus 3, and I use x equals 2, I get y equals 5. And so I get the point of intersection at 2, 5. All right, so what happens here is you have a parabola that opens down, 9 minus x squared. And then we have our equation y equals x plus 3, which is a line that has a y-intercept at 3. We know that those two graphs pass through the point 3, 0, and they also pass through the point 2, 5, like that. So those are our 2 points of intersection. I have a parabola that opens down with a vertex at 9 for the parabola. So 6, 7, 8, 9, way up here, like so. Right, and so this is a quick sketch of my parabola. Like so. And then I've got the line, right, y equals x plus 3, which goes through these 2 points of intersection right here. Right, and so this would be the function g right here, which is x plus 3, and then this is the function f right here. And what am I trying to do? I'm trying to find the area bounded by these two curves, and so we're trying to find the area of this region right here. Now, what I strongly recommend you do in problems like this is I strongly recommend you identify a representative rectangle, approximating rectangle in this region, because there's going to be situations that are going to be more complicated than this. So let me show you what I'm talking about. So let's draw in a rectangle. And what I want you to see is, so there's our representative rectangle. What I want you to see is that rectangle sweeps across the region from left to right. You know, if you could cover this region like this with rectangles like this, notice that the rectangles are always bounded by the blue curve on the top and the red curve on the bottom. Always bounded by F on the top and G on the bottom. So the rectangles, so that's a good thing. Rectangles are always bounded by F on the top, right? So that's going to be our upper curve, and bounded by G on the bottom. Right, and so since these represent this representative rectangle, no matter where you draw it in that region, as it sweeps through that region and covers it, will always be bounded by these functions, then we've got a good sense of what the upper curve and the lower curve are going to be in this problem. And see that this is also implying that sometimes we're going to look at problems where this will not happen, where the bounds on those rectangles actually change in the region. And so we're going to have to talk about how to deal with that situation. Okay, so for now, we just write that the area here is the integral from, and the x values that we're integrating between would be, x equals negative 3 and x equals 2. We're just looking at the x coordinates of those 2 points on the left edge and the right edge of that region. So we're integrating from negative 3 to 2, and the upper curve would be 9 minus x squared, put parentheses around that, minus the lower curve, which is going to be x plus 3. Then I'm going to put big old brackets around that whole thing. I think it's a good idea to actually write it out like this, put the parentheses in the right spot, especially since this is subtraction, so you don't make a sign mistake here. And please note that we're just talking about taking the upper curve minus the lower curve like this. All right, now what I would strongly recommend you do is I strongly recommend that you simplify this expression before you start trying to write down an antiderivative. In other words, collect like terms, all that kind of stuff, get rid of the parentheses. So when we do that in this problem, we get negative x squared and then minus x because of that minus sign in front of the parentheses. And then we have 9 minus 3, so that would be plus 6. And there's the function we're trying to write an antiderivative for. All right, so that's a pretty easy antiderivative. We're going to use the fundamental theorem of calculus here, and we get negative 1/3 x cubed minus 1/2 x squared plus 6x, and we are integrating from negative 3 to 2. All right, and at this point, you've got some kind of messy arithmetic here. So you have negative 1/3 times 2 cubed minus 1/2 times 2 squared, and then plus 6 times 2. And so I'll put that in brackets, and then that's minus the lower limit. We're putting in negative 3 here. So you have negative 1/3 times negative 3 cubed minus 1/2 times negative 3 squared plus 6 times negative 3. The more careful you are about plugging these numbers in when you're using the fundamental theorem like this, the less chance you have of making a careless error. I see all sorts of careless errors in these kinds of arithmetic problems here. All right, so let's go through the arithmetic. And by the way, I certainly make my share of mistakes in these, and it's because I'm not being careful. I'm thinking about the next problem after this. I'm trying to combine too many steps, things like that. Right, a classic example of not paying attention to what you're doing. All right, so you have negative 8/3 for the first term, minus, and then the next one is 1/2 times 2 squared, so that's 1/2 times 4, which would be 2, and then plus 12, put brackets around that, minus, and then the upper limit, or the lower limit, you have negative 3 cubed, which is negative 27, times negative 1/3 is positive 9, and then you have negative 3 squared, which is 9, times 1/2, 9 halves, so it's minus 9 halves, and then minus 18. And you can see, as you go through this, lots of places to make arithmetic mistakes. So area is, and I'm going to get rid of the brackets here, so you get negative 8/3, negative 2 plus 12 is 10, so plus 10. And then in the next group, I've got 9 minus 18, which is negative 9, but we're subtracting, so this is positive 9, and then plus 9 halves. And there's my arithmetic problem. So you get area is 19 minus 8/3 plus 9 halves. Again, if I've done all my arithmetic correctly there, which I'm definitely not going to say guaranteed that I'm right. I frequently will make an arithmetic mistake in here, so you have to just watch for what I'm doing here. Least common denominator is 6. So you have 6 times 19, which is 114 over 6. I think that's right. That's just 6 times 19. And then minus 16 over 6 plus 27 over 6. All right, so 114 minus 16 would be 98, and then plus 27 would be 125. And so you get the area to be 125 over 6, like so. And you could write it as a mixed number if you wanted to, certainly. As a mixed number, that would be, what, 20 and 5/6. Never a bad idea to look at the region and see if, 20 for the area for square units actually kind of makes sense. Never a bad idea to do that. So, I'm going to let you do that on your own there, but, you could certainly make little marks here in the squares and say that's 1, 2, 3, 4, 5, 6, 7, 8, 9, and then those two together maybe 10, 11, 12, 13, 14, and then there's a 15th one right there, and then the others, does it make sense that the others would add to give another about 5 units? And so, you've got most of a unit there, most of a unit there, most of a unit there. So it certainly makes sense that I would get about 20 and 5/6 as I go through and count the units in there. Never a bad idea to see if your answer makes sense in the context of the problem. All right, so there's our first example. I would definitely recommend drawing in the representative rectangle when you do a problem like this. All right, so let's go on to another example. The next example I want to look at, let's see. So, excuse me. I'm going to pick a problem out of your textbook, out of section 6.1. And so this is section 6.1, page 638 of your textbook. And this is problem number 22. And in problem number 22, you have x equals -3 plus y squared, and x equals y minus y squared. Now notice in both of these equations, and you're looking for the area bounded by these two curves. Notice that these two graphs, because they're both x equals, these are both parabolas, these are both quadratic expressions, but these are going to open left and right instead of up and down. These are not even functions of x, right? Now, we can still find the point of intersection, the same as we did before. So find, and we'll be able to sketch the graph. It's important to have a decent picture of the graph when you're going through a problem like this. So find the points of intersection. All right, so we use substitution here, and we get -3 plus y squared equals y minus y squared, like that. All right, and then let's see. So I have a y squared, and I'm adding another y squared, so that's going to be 2y squared on the left side of the equation. I subtract y, and I get minus y, and then I have -3 equals 0. So again, a quadratic that is not too bad as far as factoring. So you have a 2y and a y right here, and this would be 2y minus 3 and y plus 1. So you end up with y equals 3/2 and y equals it's y equals -1, like that. And then the idea from here is to go ahead and use one of the equations to find x for each of those y values. So I have x equals, and it doesn't matter which equation you use here. If I use x equals -3 plus y squared, then I have x equals -3 plus 3/2 squared, or x equals -3 plus 9/4. That's a 9 right there. And so you get -12/4 plus 9/4 would be -3/4. So you get x equals -3/4 right here. And there's our point of intersection, is at -3/4, 3/2. And then for y equals -1, we'll use the same equation. It doesn't matter, again, which equation you used. So you have -3 plus -1 squared. So that's x equals -3 plus 1. X is -2. And so this point of intersection is at -2, -1. All right, so let's see if we can get some sense of what this graph looks like, what this region looks like, and then see if we can write out the integral. So you have -3/4, 3/2 is one point of intersection. So -3/4 and then 1.5. So that's somewhere right about in here. And then -2, -1 is right about there. All right, and so we've got, what we have are two parabolas that go through those 2 points. If you want to, excuse me, if you want to get some sense of how this is going to work, you could take the first equation, x equals -3 plus y squared. Let's see. So you have x equals -3 plus y squared. You could substitute 0 in place of x. So you get y -3 plus y squared equals 0. So you get y squared is equal to 3, or y equals plus or minus the square root of 3. So on that graph, and we'll put this one in red, the x-intercepts are at about 1.7. I'm sorry, the y-intercepts there are, because you're going to get 0 plus or minus the square root of 3 there. So you get one right about there and one right about here, like this. And we also get, that the vertex of this parabola, if you let y be 0, you get x equals -3. And so you can see pretty clearly, the parabola that you're getting for this one graph. All right, this parabola looks like this. Okay, so that's x equals negative 3 plus y squared. And then x equals y minus y squared. Let's have a look at that one. So x equals y minus y squared. First of all, you could factor out a y there, and you get 1 minus y. And notice when x is 0, you get y is 0, and you get y equals 1. So you get 0, 0. This one goes through the origin, and it also goes through 0, 1, like that. We'll put this one in blue. So it goes through the origin, and it also goes through 0, 1. So 0, 1 would be like right about here. And if you wanted to substitute in some more y values, you certainly could to get a better idea of where this graph is gonna look. So like if you substituted in y equals 2, for example. Let's just do that real quick. So if you substituted in y equals 2 into this equation, you get x equals 2 minus 4, or negative 2. So you get the point negative 2, 2. Okay, so negative 2, 2 is up like this. And then if I substitute it, so that's y equals 2. If I substitute in y equals negative 2, I get x equals negative 2 minus negative 2 squared. So you have negative 2 minus 4, or x equals negative 6. So you get negative 6 for the x value, and the y value is negative 2. You're down over here, like that. And that, I should probably put that one in blue also. Right, and so you're starting to get an idea maybe of what this graph is going to look like. If you wanted to, you could certainly complete the square to find the vertex of this parabola. You could use x equals negative 1, or I'm sorry, y equals negative 1 if you wanted to get another point if you weren't sure. Using your graphing calculator would certainly be fine here. If you use y equals negative 1, you get x equals negative 1 minus negative 1 squared, or x equals negative 1 minus 1, or negative 2. So you get the point negative 2, negative 1. So negative 2, negative 1 goes right there. Right, and so you can start getting an idea of what this parabola is going to look like. There's going to be a vertex in here somewhere, and this parabola is going to look like this. Right, and so we are looking for the area of the region bounded between these two curves, right, and that's this area right here. Now, in a problem like this, what I want you to notice is that if you use representative rectangles, like we've been talking about, there's a problem here. And the problem is that, notice if you, I'm drawing vertical rectangles now, so if you draw a vertical rectangle over here, and a vertical rectangle over here, notice that those two rectangles have different curves bounding them. So the vertical rectangles have different curves bounding the top and the bottom. That's a problem. Now, it's not something we can't get around. We could certainly do that. And sometimes there's no way to avoid it. But in this case, we could completely avoid that issue by using a horizontal rectangle instead. So I'm going to put this one in green, and notice if I draw this horizontal rectangle, the horizontal rectangle always has the same bounds as it sweeps from bottom to top. So the horizontal rectangle always has the same bounds. So we're going to try to use horizontal rectangles for this integration problem. Now, when you do that, when you use horizontal rectangles, the width of this rectangle, in this case, is a delta y. It's a change in y, right? And so you're integrating with respect to y in this case. And so when you draw a horizontal rectangle, and sometimes that's the way to go in a problem, you're going to integrate with respect to y. All right, now remember what the points of intersection were also. Let's go ahead and put those in here. You know, this was at -2, -1, this point right here. And then the other point was at -3/4, 3/2. That's that point right there. All right, that's important when we're setting up the limits of integration. So the area on this problem, all right, just like we've been talking about upper curve minus lower curve, when we're integrating with respect to y, the way to look at that is it's kind of like you're turning things around, and this is going to be right curve minus left curve. That's kind of the equivalent way to look at upper curve minus lower curve when you're talking about integrating with respect to y. It's right curve minus left curve. So in our problem, what's our area going to be? It's going to be the integral, and the right curve on that horizontal rectangle, that green horizontal rectangle I have, is our blue rectangle, and that blue rectangle is given by x equals y minus y squared. And so this would be y minus y squared. That's our right curve. And then minus the left curve, which is our -3 plus y squared. And that'd be dy. And again, this would be the right curve in this region, and this would be the left curve. The limits of integration here, be careful, we're integrating with respect to y, so these are going to be y values, and this is going to go from -1 to 3/2, like that. All right, so this is our first kind of foray into integrating with respect to a variable besides x. Now from here, it's the same problem we've been doing. You're integrating from -1 to 3/2, and just collect like terms. So you have -y squared minus y squared is -2y squared. And then you have positive y, and then plus 3. And so that it's not a hard integral, but that's what we're going to write. Be careful with the signs when you're collecting like terms here. And so this would be the integral from -1 to 3/2. And this would be, and I don't need to do that anymore, right? Because I'm ready to write down the antiderivative, so I can do that. So might as well do that, right? And so this would be -2/3 y cubed plus 1/2 y squared plus 3y, and that would go from -1 to 3/2. So at the upper limit, put brackets around this, you're going to get -2/3 times y cubed, so this would be 3/2 cubed plus 1/2 times 3/2 squared plus 3 times 3/2. Close the brackets off, minus, put brackets again for the lower limit of integration, and this would be -2/3 times -1 cubed plus 1/2 times -1 squared plus 3 times -1. Notice how I'm really careful to just kind of substitute things in, not to do a lot of arithmetic in this step. And then, what I'm going to say from here is the rest of this is arithmetic, and so I'm going to put ... I'm going to cheat and put ... there and say, you finish this. The rest of this is arithmetic, right? We've done the calculus in this problem. All right, so this problem has had a few wrinkles in it that we hadn't seen before. So let's now go on to a problem like this one. So we're still back in the textbook here, and I was going to look at, let's see, there was a problem in the textbook I wanted to look at in particular, I felt like. So, well, now I don't seem to be able to find it, so that's okay. let's go ahead and look at problem number 29 to kind of finish out our discussion on area between two curves. And then I have a picture or two to draw at the end here. So this is number 29 of the textbook, and this is page 638. And the two curves in this case are x equals y cubed plus 2y squared plus 1, and x equals negative y squared plus 1. All right, so we want to get an idea of the picture, certainly at least try to get some sense of what this is going to look like. Points of intersection, certainly, we're trying to find the area bounded between the between these two curves. Okay, and so the points of intersection are going to be, let's see, we use substitution, we get y cubed plus 2y squared plus 1 equals negative y squared plus 1. Okay, so this gives me y cubed plus, I add y squared and I get 3y squared, and I subtract 1 and I get 0. So I factor out a y and I get y times, I factor out a y squared and I get y squared times y plus 3. And so that gives me y equals 0 and y equals negative 3. All right, so if I use the equation x equals negative y squared plus 1, when y is 0, we get x equals 1, and we have a point of intersection at 1, 0. And when y is negative 3, I get x equals negative, and then this is negative 3 squared plus 1. So this would be x equals negative 8. Right, that would be negative 9 plus 1, or negative 8. And so I get a point of intersection at negative 8, negative 3, like that. All right, so those are my 2 points of intersection. Now I know what x equals negative y squared plus 1 looks like. Right, that's a parabola that crosses, when y is 0, it crosses at x equals 1. Right, and so certainly you have a parabola for that one. Let's see, and I shouldn't have put the curve like that because I'm not going to fit it in there very well. So here's my y-axis, and here's my x-axis. And let's see, I have a point of intersection here at 1, 0, and another one at negative 8, negative 3. 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3. Here's negative 8, negative 3, like this. All right, so 1, 0, that's the vertex for x equals negative y squared plus 1, and if you use, for example, if you used y equals 3, for example, you're going to also get negative 8 for that one. So, here you get this graph, and we have intercepts there at 0, 1, and 0, negative 1. So here's the parabola. And then we have this cubic function, x equals y cubed plus 2y squared plus 1. And remember, we've got points of intersection here, right here and right here, right? So we've got this cubic graph. And so, you want to try to sketch that cubic graph and see where it's located. Now, you might want to, if you didn't have, I'm going to look at a graph on this one in a second, on my graphing app, but if you didn't have that available, or you didn't have a graphing calculator, what you might do here is you might just pick some y values for this equation. So you have x equals y cubed plus 2y squared plus 1, and so picking y equals negative 1 and y equals negative 2 makes sense here. So you have x equals negative 1 plus 2 plus 1, which is 2. And so you have 2, negative 1 is a point on that graph. And then you have x equals negative 2 cubed, which is negative 8. And then negative 2 squared is 4 times 2 is 8 plus 8 plus 1. And so you get negative 2, 1 for that one. Okay, so let's see. We're going to put this one in blue. And so you have 2, negative 1. Let's see, so 2, negative 1 goes right here. And then -2, -1. So -2, -1 goes like right here. I'm sorry, that's -2, +1. That's better. I knew there was something not quite right there. So there's -2, 1, like that. Okay, that's better. Right, and so we're looking at what this cubic graph might look like. And so if you're not sure, you know, at this point you need to either plot more points. You could graph on your calculator. If you graphed, like on a TI-84, for example, if you graphed y equals x cubed plus 2y squared plus 2x squared plus 1, right? That's not the same equation, but it does give you a sense of what the shape of this graph would be. If you have a technology that does not graph something implicitly, right? So now I have something that will do that, implicitly. Okay, it'd be nice if I kind of knew what I was doing here. I'll get it eventually. There we go. And I'm going to go ahead and graph in 2 dimensions. And I'm going to graph, let's see, an implicit function, right, like this. So I can graph something implicitly here. And so this is x equals y cubed, y raised to the 3rd power, plus 2y squared plus 1, plus 2y squared plus 1. So there's one graph. I'm going to put that like in red right there. So I'm going to look at that graph, and there's that graph, right? I'm going to turn off this parabola here because I don't want that one. And I'm going to do another implicit graph. I'm going to do negative y squared plus 1. So negative y squared plus 1. Do this one in blue. Oops. Oh, and I didn't put x equals there. So let me put that in there. So x equals, save that. And so there's my graphs. And if you look at those, sure enough, the graph does fit in with what we've talked about. And so we can, we get some better sense of what this graph looks like. Now we do have a point of intersection at 1, 0. We also have a point of intersection down there at -8, -3, like we talked about. All right, so looking at this graph right here, oh, I knew there was something that wasn't quite matching with that graph right there, but this point is wrong. That's what it was. There, the x value is 1, and I don't think I'm going to edit this out because it's probably good for you to kind of see that I was trying to reconcile this picture with what I just saw on my app there. So you have the point x equals 1, and then y equals -2. Okay, so now that fits better. There we go, like this. And so we have this cubic graph coming in like this. And then the cubic graph comes through like this. And so the place where we're looking at trying to, let's see, try to fit this shading in a little bit better here. This is the region we're talking about. And y'all see that if you tried to use a vertical rectangle, again, the vertical rectangle just doesn't work for us in this problem. And the reason why it doesn't work is because depending on where you draw it, you have different bounds on that vertical rectangle. If I draw one there and I draw one over here, both are in the region, but they're bounded by different curves. That's bad, right? Instead, I use a horizontal rectangle, and if I use a horizontal rectangle here, the bounds are always the same. The blue curve bounds on the right side, the red curve bounds on the left side. And so that's what I do here, is to find this area as I use a horizontal rectangle. And go ahead and integrate with respect to y. Okay, so since I'm integrating with respect to y, remember this is going to be right curve minus left curve. All right, so the area of this region would be the integral from, remember that these points of intersection are at -8, -3, and at 1, 0. So we're going to integrate from -3 to 0. The right curve is our cubic graph, and so that would be y cubed plus 2y squared plus 1, minus the left curve, which is the parabola, and this is -y squared plus 1, like this. And this is the function that I'm integrating. All right, so we know what to do now. We go ahead and collect like terms. I definitely collect like terms before you start integrating here. So this is this is y cubed, and then plus 3y squared, and then the ones cancel, and so you're just left with y cubed plus 3y squared dy. So not too bad. And so then the area would be 1/4 y to the 4th plus y cubed, and this would go from -3 to 0. And the convenient thing here is that the upper limit, this is just 0. You just get 0 plus 0 minus the lower limit. So be careful about the lower limit, and you get 1/4 times -3 to the 4th plus -3 cubed. And so when you go ahead and multiply this out, so let's see, you get -3 to the 4th is 81 positive, and then times 1/4, so it's 81/4, and then that's negative because of the negative sign up front. And then you have -27, but that's going to be plus 27, like that, because you're subtracting that. Make sure that you get a positive answer here. I see students all the time make a mistake and get negative answers. A lot of times when you have a negative answer on an area between two curves problem, it means that you subtracted the curves in the wrong order. You did lower curve minus upper curve, or left curve minus right curve, possibly. All right, so then finally, -81/4 plus, and then the least common denominator is 4. And so this is 108/4. And so you get the answer to be 27/4. Which is a little bit bigger than 6. Again, not a bad problem to kind of count out some rectangles there and see if 6, a number bigger than 6, a little bit less than 7, makes sense in there. But I think you'll find that that does make sense. So, all right, so that gives us a problem, another problem to take care of there, or taken care of. All right, so now let me just draw a picture here to kind of finish this up. If you've got a somewhat more complicated situation. In other words, you have the area, let's say you have a curve that looks like this. Let's say it's just a line, but then you have another curve. We'll put this one in red. Like so, and you're asked to find the area, let's say that this is G, and this function here is F. And you want to find the area between, or bounded by, I should say bounded by G and F, and x equals 1, and x equals, let's see, 1, 2, 3, 4, 5, 6, 7, 8. Let's say x equals 9. Okay? Well, so the region you're talking about, here's x equals 1, and here's x equals 9 right here. And so the region you're talking about is a region that kind of looks like this. Now notice in this case, so here's our region. There, and then this piece also right here. All right, so to find that area like this, notice that the upper curve and the lower curve switch out. Now, using vertical rectangles makes sense here, but what happens? When you draw this vertical rectangle, the red curve is the upper bound, but when you draw this vertical rectangle, the black curve is the upper bound, like that. And so what happens is, in this particular picture, you need two integrals to find the area here. The upper curve and the lower curve, in other words, switch around. So the area would be the integral from, and this is at x equals 1, and 2, 3, 4, 5, 6. The point of intersection of those two graphs is at 6. And so we'd integrate from 1 to 6, and the upper curve in that region, in that interval, would be g. And this would be g of x minus f of x. And then we would integrate from 6 to 9. And in that case, the f curve is the upper curve. So you have f of x minus g of x there. So you'd have to use two integrals to write out this area right here. Now, in the exam, I'm not going to give you anything like that. I won't give you anything that complicated. I want to be just have a very introductory example here. It's not going to be too big a deal. But I did want to give you some examples of some area between two curves problems out of section 6.1. If you're looking for practice problems out of the textbook, there are some, by the way, some practice problems in the final exam review. But if you want to look at practice from the textbook, I would look at page 637 of your textbook, and I would look at anything from really problems 1 through 11, and then problems probably like 15 through 23. Those would be good practice problems. That's good practice. All right, so this marks the last lecture of the semester. Please let me know how I can help you the rest of this week as you prepare for the final exam. Remember that there's a take-home problem. Oh, the take-home problems for exam 3. No take-home problem for the final exam. But one thing I do want to remind you of on the final exam, remember, is that I do allow the use of a 3x5 note card. So on the final exam, you have a 3-inch by 5-inch note card, and you can put anything on there you want, and I would spend some time trying to put together a note card for the final to help you out with remembering certain things that maybe you have trouble remembering. So please talk to me if you're having some questions about what to put on a note card like that. Have a great day. Good luck this week. Let me know how I can help you. Thank you.